Swayam Prabha. Digital India. Educated India.
So, hello everyone. Now we will continue with the fibrogram. Here we will try to understand the superimposition of the fibrogram and shorter diagram, and which parameter is actually responsible for change in shape. Now try to see here, if we draw for cotton, the fibrogram is this is the fibrogram, but comb shorter diagram, this is the proportion, this is the length, but in comb shorter diagram the shape is in this fashion. This is where is the length and this is the proportion. Okay. And what will happen if we try to superimpose? Now try to see, this will make us our understanding clear about the change in shape. Now there are two axes, one is green color and this one is red color. So green color shows the proportion of fiber, and so where proportion of fiber is in y axis and length is in x axis, that is fibrogram. Okay, so fibrogram, typical fibrogram of cotton is this is the typical shape. Now let us see the shorter diagram. So red color axis is that the length, it shows the length, and green color shows the proportion here. The shorter diagram, which is shown in the dotted, green dotted line. Now if we try to superimpose, we are now superimposing these two curves, then you just see we are just superimposing the proportion axis with the proportion axis and length axis with the length axis. Now we can see here very well the same fiber, same fiber, and the length, you can see typically length is almost same. Okay, end point of the length is almost same and end point of the proportion is almost same, like 100% fibers or maybe certain, this is the proportion, this almost same, but at the midpoint we can see its shape is entirely changed, and this change is mainly due to two factors, as it is basically length biased sampling and also due to the folding. And this concept one has to be very clear. So whatever we are measuring in the fibrogram, it's not the actual length. We are selecting the longer fiber preferentially, and then again we are folding it. So that's why the shape for the same fiber, the shape is different. Okay, now if we imagine the during the fibrogram, what we are doing, we have developed one system which will pick the fibers. So earlier normal case, what we are doing, we are selecting the preferentially the longer fiber, okay, and there is a fold. That is, now imagine we have selected from a fiber mass, we are selecting all the fibers. The device we have developed which is able to select all the fibers together. And also the special device is that where only the tip point of the fibers are selected. Okay, only the tip points of the fibers are selected. So this is the tip points, no folding. This is the clamp of fibrogram, no folding. And this is the folding, as we know. This is a normal, this is the normal is A, and here it is a B with a new technique. Now the shape of the fibrogram of A is normal. This is the shape of the fibrogram. Length, and this is the, sorry, this is a proportion, and this is the length, fibrogram. But if we take the fibrogram of this, when we have picked the fiber, when there is no fold, pick the edge of the fibers. In the case of B, some new imaginary technique which has not yet been developed. In that case, the shape will be here. If it is the proportion, it will be just like a fibrogram. This is just like a fibrogram. Although this will, this is a, this will be shaped like a shorter diagram. The shape will be, shape will be like shorter diagram, although it's a fibrogram. So that means that the difference in this shapes of fibrogram and shorter diagram is mainly due to this loop formation, folding of the fibers. But by different analysis, different standard parameters like uniformity ratio, uniformity index, we have already discussed, mill length, upper of mill length, span length. So we can express the parameters, and which is shown in this diagram. So shorter diagram is, this one is shorter diagram, and this is a fibrogram. And if we superimpose these two, we will get this type of shape. And this zone length compromise, here we are compromising the length in the fibrogram. So this much, this zone we are compromising the length, and this length compromission is due to the folding of the fiber. Okay. So the shape of the fibrogram and shorter diagram one has to be very clear for analyzing. Similarly, for the man-made fiber with the equal cut length, the shape of the fibrogram we have already discussed, it is a triangular shape, and shorter diagram is a rectangular shape. And when we superimpose, these zones are mainly due to the folding of that. Of fiber. Now let us try to draw the curve. What we have done, we have actually the curve we have got, the graph like fibers shorter diagram or fibrogram we have got, and from there we can calculate the different parameters. We can calculate the 2.5% span length, 50% span length, uniformity ratio. Now let us do in the reverse way. From that we will be doing, but here in this problem we can do. So if we have some data given, like effective length is given, maximum fiber length is given, dispersion percent is given, can we draw a typical diagram? So that we will see, but this example is that from the given fiber shorter diagram and fibrogram of a typical cotton fiber, calculate the following parameters. We have to calculate the following parameters: diagrams, shorter diagrams and typical cotton fiber, that is for a typical cotton fibers are given. So shorter diagram and fibrograms are given. We have to calculate the dispersion percent, short fiber percent, uniformity index, uniformity ratio, effective length and 2.5% span length. So let us see, these are the diagrams available. Now we have to calculate, say measure the 6 different parameters. Now let us see which parameter we can get from shorter diagram, shorter diagram. Dispersion is the parameter which we will get from the shorter diagram. Short fiber percent we can get from the shorter diagram. Uniformity index from fibrogram, 2.5% span length from fibrogram, effective length we can get from the shorter diagram. And from fibrogram we will get the uniformity index, 2.5% span length and uniformity ratio. Now what we will be getting, the typical value, okay, typical value, it will exact value, there will be some error. So let us first try here, okay. Dispersion percent and effective length. Let us see what we have to do. This is the shorter diagram, okay, and as per the here maximum length is 35 mm, what we have to do? So 35 mm, you have to take the midpoint of this. So 35 mm, so we are taking midpoint. Okay, this is the midpoint of that. So from this midpoint we have to draw a horizontal line, first approximation. This is the point, so P. Okay, and we take the 1/4 of, say this is OP, 1/4 of OP, this is a Q, 1/4 of OP. Then we take another line which is Q dash, so this is P dash. Okay, and then we take again half of this, we draw another point. We have discussed already this horizontal line which is M. So 1/4 of OM we are taking N, so ON is 1/4 of OM as per the definition. Then we draw this line N dash. N dash is the effective length as per the definition. So we can see that this is typically, say, 26 millimeter. Typically 26 millimeter. Now 1/4 of OM is ON. Now another part we are taking this R, so OR. R dash is the, so OR is 3/4 of OM, that is upper quartile. So R dash will so this is lower quartile. R dash is the lower quartile length. Now R dash, again we draw one line here, horizontal line which is intersecting N dash. So interquartile range will be, so R dash is lower quartile length. We can see that the value is typically around, say, 20 millimeter. So 20 millimeter. So interquartile range will be, effective length is 26 mm. So dispersion percent, this is the dispersion percent will be, as per definition, 26 minus 20 by 26. So 6 by 26. So this will be 6 by 26. This will be typically 23.07%. So this is the dispersion percent we have got. Effective length is 26. So if dispersion 23% and effective length. So here, if the curve is given, we can calculate the, so one thing is we have missed, so dispersion percent and short fiber percent. Short fiber percent was, this is the, and here we can take the, this length, and from there this is the length, and say O, say P and Q. Here what we can do in the basis of, on the basis of number, we can, if we want to measure, so PQ by OQ. This is a short fiber percent. So short fiber percent is the total. This is the zone. So dispersion, short fiber percent, and effective length we have calculated. Now coming to the fibrogram. So uniformity index, uniformity ratio, and 2.5% span length. So typically approximately say 2.5 point is this one. Okay, now we measure this point. So this is the length, is the 2.5% span length. It's typically around say 29 millimeter is 29 millimeter is a 2.5% span length. Okay, and uniformity ratio you have to calculate. Uniformity ratio, now 50% span length if you want to measure, so 50% span length is typically say 7 centimeter, 7 millimeter, 7 millimeter. Okay, 7 millimeter. So 7 by 29, uniformity ratio will be 50% span length by 2.5% span length, 100. 7 by 20, 24.13. 24.13% is the uniformity ratio, which is lower side. Okay. Now next is the uniformity index. Uniformity index is that, which is, we know that mean length by upper half mean length, and mean length is defined by the, so what we have to do, you draw a tangent here. So mean length is typically 11 mm typically, and upper half mean length you draw from 50% point, typically 28 mm. So 11 by 28 multiplied by 100, it will be 39.28. So this is a rough parameter, but as we have seen, we have discussed that uniformity index should be around 75%. So that this is the curve is drawn. It's not actual curve, but typical step we have tried to explain. So one can analyze the existing sorter diagram and fibrogram to calculate different parameters. But although the instrument, the fibrogram, from fibrogram we can get automatically the things are calculated, the parameters are calculated, but one should understand how to calculate, why, how is it being calculated. Okay, so that's why we have done this part exercise. Next is that, as we have discussed, the parameters are given. Parameters are given, we have to draw the curve, and from there we have to calculate the short fiber percent, approximate mean length of the blended fibers, approximate uniformity ratio of blended fiber. So let us do one by one. So 50-50 polyester cotton, in actual scale we have to do. First let us try to do the comb sorter diagram. So we will take a graph paper, and in graph paper we have to, in comb sorter diagram we should be actually taking this x axis, y axis properly. Sorry, let me draw once again. In comb sorter diagram, here it's a proportion. Length 50-50 polyester. So 10 millimeter, 20, 30, 40, this is millimeter. (50-50) polyester cotton. Typical comb sorter with effective length of cotton and cut length of polyester. This is important. So effective length, we will just roughly try to locate the effective length. So effective length is 36 millimeter. Then maximum length of cotton will be more than that. So effective length is 36 millimeter here. So maximum length will be definitely more than that, say around 42 millimeter. This is 42 millimeter, and let us draw. This is the, let me draw it once again. This is the cotton, and polyester is 36 millimeter. So this is the polyester, and here polyester we can draw it in different color. So green color, polyester is there. Now first we have to draw it neatly, draw a typical comb sorter diagram. Now actual scale typical comb sorter diagram. So comb sorter diagram, as we have already seen, so that we can draw here. The cotton portion will be little bit higher, then polyester part, then cotton part. So this is 36 millimeter. So this is polyester, and then rest all are cotton. Typical comb sorter diagram. Now what we have to calculate? Anything from the comb sorter diagram? Effective length of cotton with this is done. Okay, and the dispersion percent. And now when we draw the comb sorter diagram, what we have to take care also? The dispersion percent. So this is the effective length, here is the effective length, that is, and the upper quartile part should be the 25%. So lower quartile, say this is the lower quartile part. So effective length is 36 minus lower quartile divided by 36, 100 equal to 25. So lower quartile we can calculate. So what will be the lower quartile? 36 minus L equal to 36 multiplied by 0.25. So L will be 27. So this is the 27. So we have to set the point here in this fashion so that it's a 27. This is 27 millimeter and this is 36 millimeter, so that we can get the dispersion percent of 25%. So first we have to draw the individual curve, then we have to draw the combined curve. So individual curve is important, and from there it's this is the curve we are drawing. And next is that next point is here the fibrogram. Now fibrogram for polyester is 36 millimeter cut length, proportion, and here is the length. Now for 36 millimeter, 10, 20, 30, 40. So 36 millimeter is at this point, and proportion we can say there is a 50%, 100%, 2.5%. This is the fibrogram. And if we see the cut length is 36 millimeter, there will be one fiber which will be maximum, and we just simply join these 2 points. We will join this 2 point from 100% to 36. This is a typical curve for polyester. Now for cotton will be in between somewhere. For cotton with a uniformity ratio 46%. That while drawing the curve for cotton, we should take care of this. So 2.5% span length will be little bit less than 36 millimeter. Let us say it is 30 millimeter. 2.5% is 30 millimeter, and if 2.5%, this is rough calculation, so 36 millimeter, then to have 46% uniformity ratio, so 36 by span length to 50% equal to 0.46. So span length 50% will be 36 by, sorry, I am making mistake. So uniformity ratio will be 46% equal to 50% span length by 36. Span length 50% will be 46 multiplied by 36 by 100, 16.56 millimeter. So 50% span length we know, and here 16. At this point, this is the point. So 16 is the 50% span length from this point, and we have total. We start with this and we will go through this, and this is the typical curve for cotton. Polyester we have got straight line, and cotton we have got, we can now, as it's a 50-50 blend, what we will be doing, the blended mass, the typical curve will be in between the polyester and cotton. We can draw roughly a curve. This will be definitely in between polyester and cotton, and what we have to calculate, blended mass, cut length of typical uniformity ratio is the diagram. So short fiber percent of cotton, approximate mean length of blended fibers, these two will come. Short fiber percent, as we have already discussed, it is from the shorter diagram, and mean length. So mean length we can get from this curve. You draw the tangent from this, from the 0 point on the blue curve. So this is the mean length by the shorter diagram, sorry, by the fibrogram, and approximate uniformity ratio of the blended portion. So this was the cotton, approximate blend uniformity ratio will be, this will be little bit higher. So earlier it was 16.5, so it will be say 17 by say 36 into 100. So typically around 17. So what will be the uniformity ratio? Sorry, 47.2%. So earlier it was 46%, now it has become 47.2%, mainly due to the blending with the polyester. So okay, so this way we can analyze. Next, the HVI test results of cotton are given. Upper half mean length 40 millimeter, mean length is 25.7 millimeter. Uniformity index, it's a simple, uniformity index will be 25.7 by 40, upper half mean length by upper half mean length multiplied by 100. We can express the uniformity index in terms of fraction or in terms of percent. Okay, so it will be 64.25%. Next is that 2.5% span length and 50% span length are given. So, uniformity ratio has to be calculated. So, 50% 0.5 inch, the 50% span length divided by 2.5% 1.25 multiplied by 100. It will become 40%. So, you can see here. So, these are the small one step numerical. So, you can express in terms of the fraction also. Okay. Typically, both the way you can express. Another similar numerical, 50% span length is given, uniformity ratio is given. So, 2.5%. So, uniformity is 45% and 15 by S 2.5 multiplied by 100. S 2.5 equal to 15 by 45. So, it will become 33.33. 1/3, 33.33 millimeter. Okay. So, this will get cancelled out, 3 will be there. So, 100 by 3, 33.33. So, in this way we can go on calculating. Our next numerical is 50% span length and the uniformity ratio of a cotton fiber are 12.6 and 48%. The similar problem. So, 50 equal to 12.6 divided by S 2.5 span length 100. S 2.5 will be 12.6 multiplied by 2. It will be 25.2 millimeter. Okay, it is assumed here, it is written. So, 48%. So, this is a 48%. 48%. If we considered it's 48%, then the uniformity ratio is given 48%, which was earlier. So, for if it is 50%, then it will be 25 point, and 48% we are getting this. 2.5% span length is 26.25. Another numerical, upper arm mill length is given, 50% span length is given, okay, and mill length is 25.6. If the ratio of uniformity index and uniformity ratio is 2.25. So, here the ratio is given. So, uniformity index is mill length by upper half mill length, and uniformity ratio is 50% span length by 2.5% span length. Ratio of uniformity index and uniformity ratio. So, uniformity index by uniformity ratio is mill length multiplied by 2.5% span length by upper half mill length multiplied by 50% span length. So mill length, upper half mill length is given. This data is given. Upper half mill length is here 41 millimeter. 50% span length is 12 millimeter, and mill length is 25.6, and the ratio is equal to 2.25. So 2.5%. So from here 2.5% span length, this is required, equal to 2.25 multiplied by 41 multiplied by 12 divided by 25.6. Sorry, 43.2 is the answer. So this should be the answer. So what is that? It's a 2.5% span length is 43.2. Let us see. So stepwise, uniformity index is given. You can calculate. Then from then 43.24 is the answer. Okay. So this type of numerical one can always try, and it one should try to do based on the actual data from the fibrogram. Next is that same problem. If the 2.5% span length is given and uniformity ratio is given, so 35% uniformity ratio, that 50% is 50 by 2.5%, 3500. So this 35 is the 2.5% span length. So S 50%, span length 50% is 35 multiplied by 35 by 100, 12.2. So this way one can try to calculate 12.25. Okay. These are very simple numerical, but one should practice. Next is that the result of a cotton fibrogram is given. Upper half mill length, 50% span length, mill length. Again, if the ratio of uniformity index and uniformity ratio are this, so again we should see. So uniformity ratio of uniformity index. Uniformity index by uniformity ratio. Uniformity index means or mean length 30.4 by upper half mill length 38.5 divided by 50%, span length is 18 divided by S 2.5 equal to 1.8. Okay. And now 30.4 multiplied by S 2.5% divided by 38.5 multiplied by 18 equal to 1.8. S 2.5 would be 1.8 multiplied 38.5 to 18 divided by 30.4. So we will get a result which is already calculated. So you can see here we will get 41.03. So the calculation you can do stepwise. Now we have to calculate the uniformity ratio of fibers of equal cut length. Now what we have seen, we have calculated the uniformity ratio of cotton, but cut polyester fiber uniformity ratio. So what is uniformity ratio? 50% span length by 2.5% span length. Now for typical cut fibers are equal cut length fibers. This is the shape where this is the proportion of fiber, percent fiber, and this is the length. Now here O A B, this is a triangle OAB. It is forming a triangle OAB. Now at the 50 half point, we are drawing one line which is 50% span length, CD, and 2.5%. So OB is, if OB is 100, OC equal to BC will be 50%. Now this is 2.5% of that. So that means OBCD E is the point. So BE will be 97.5. OE is 2.5. Okay. So in that way, and EF, what is uniformity ratio? CD by EF. If we take this fraction, CD as per definition 50% span length, which is CD, and 2.5% span length is EF. So as per definition, CD by EF, and CD by EF is there. Now the triangles BEF and triangle BCD and triangle BCD and triangle BEF, they are similar triangle. The similar triangle rule is that where CD, as per the similar triangle, CD by EF will be equal to CD by EF will be equal to BC by BE, BC by BE. So CD by EF is nothing but uniformity ratio. BC is 0.5 of OB and BE is 0.975 of OB, 97.5% of OB. So 0.5 divided by 0.975, 0.51 is the uniformity ratio of a fiber of equal cut length. That means we can always see the cotton with variable fiber length cannot have the uniformity ratio more than 0.51. 0.51 is the maximum uniformity ratio possible for a fiber, where the ideal fiber distribution is that all the fibers are of equal cut length. Okay, so the problem here is actually discussed and we have got the value 0.5128. So the same thing has been discussed here. So uniformity ratio here, as per this, uniformity is CE by DF. Okay, DF is the 2.5% span length, CE is 50% span length. And here see AOB is also equal triangle, but here ACE and ADF, this triangle, between this triangle we can get this relationship. Okay, we can get the relationship of, so CE, which is 50% span length, and DF, which is 2.5%, this is uniformity ratio, and AC and AD, AC by AD. Okay, between this we will get the uniformity ratio. Now we have discussed the cotton fibers length analysis. So another fiber which is important as far as length measurement is concerned, that is the wool fiber. The wool is also a natural fiber and length variation is there. So we have to measure the wool fiber length measurement. Now what main difference in principle between the measurement of fiber length of wool and cotton are that cotton fiber length we can measure using the photoelectric method, like a high volume instrument, in fibrogram we use the photosensing. But the cotton fiber, what we have discussed, that the fibers can be the length is measured based on photoelectric method, because we can prepare a very fine fringe from cotton fiber, and where the light can pass through and we can measure the difference in the density of the light passing through. But if we consider the wool fiber is very bulky fiber, where the fringe of very fine thickness, it is not possible. And suppose in case of cotton, we are making a fringe, and the principle of measurement, automatic machine, is typically for cotton is a photoelectric method, where light passes through and we can measure the number of fibers or density of fibers, that we have already discussed. But for wool, the main problem is that wool is very bulky, so we cannot produce very thin fringe. Suppose this is the wool fringe through which light does not pass, and in between this fringe there will be short fibers and also long fibers. So, the technique of light scanning cannot be applied in case of wool fiber. So, one should very clear that if we try to use the same technique for wool fiber, we will get wrong result. So, for that, wool fiber length measurement is done using the capacitance method. Okay. In capacitance method, we can identify the quantity of fiber. The capacitance is proportional to the quantity of or mass of material present. So, here although light does not pass through this, but the capacitor plate can identify the difference in mass or quantity of fiber, and quantity of fiber is proportional to the fiber length. So, accordingly we measure the fiber length of wool. So, capacitive method is used. A sample of wool is taken and then are made parallel. So, the fibers are, so this is the fiber. So, we make a fringe like this, fiber fringe is taken, one end is sealed in between a plastic strip. So, special plastic strips are available, and then we draw this plastic strip through a capacitor plate, and change in capacitance is calculated, which is proportional to the mass or number of fibers present. This is the system here, this measuring slot which works in capacitance principle, and we start drawing. Okay, we draw. This is nothing but it's a plastic slate, plastic film. This is not fiber. Fiber is from the end point. So here one thing is that the fibers are gripped at the end point. So fibers are gripped here, and then we are it is passing through the measuring slot, and we plot a curve. This fibers, the fringe is called a draw, and this draw is pulled through the slot. Capacitance method. Now let us see the animation. Now the fiber is drawing through the slot, and we are getting the points. Initially 100%, whatever capacitance its reference is 100%. That point we are not recording. 95% of that point we start and go on recording at the interval of 10%. 95% of the initial capacitance, then 85, 75. In this way, we are getting a number of points, and in x-axis it is showing the cumulative frequency, and in y-axis whatever length we are drawing, this is plotted. This will look like approximately similar to the shorter diagram, but here principle is that is the capacitance principle, and from this cumulative frequency diagram we can calculate the mean length. Here we can get the mean length. This is the cumulative frequency, and the mean length is drawn based on the, so this is between the 10% interval between 5% to 95%. So we just take the length L1, L2, L3, L4. In this way we take the length at different point and add it and divide it by 10, because at the 10 intervals we are taking, we get the average mean length of wool fiber. And there is an automated version of this. This is a manual version, and automated version is actually called the almeter, where it has got two components. So in its first part I told that we have to make the fiber fringe where the end point of each of the fibers are gripped. End points are gripped. Only end points are gripped. Okay, and then we are scanning it, and here in this machine, as it is automatic machine, here the fibro liner is there, which forms this type of fringe automatically, and the initial fibers in the sliver form is kept at the bottom comb, and then one by small at the small portion. So suppose this is the fibers kept in the bottom comb. Now the fibroliner, the grip is gripping a small quantity and putting it in on the top cone. Then again next it is putting in this way, it's keeping on doing, and when the one by one the then this is when this all these fibers are exhausted, this comb will drop and then again it will keep on taking the next fiber. So always it is gripping the end point and arranging the fiber in the top comb, and then this fiber fringe which is created, so this fiber fringe will be just like end point is there, that this will be the fiber fringe, and this fiber fringe is actually then clipped by the two plastic sheet and which is placed on, then subsequently placed on the measuring unit. So you can see here sample, the trapped between two plastic sheets at a constant speed with a longer fibers entering in the capacitance path. So in that way tip is entering at the first, so then it will scan and automatically it will calculate the fiber length parameter. But as I have mentioned, the principle here is the capacitance principle. This is the L meter. So changes in capacitance is caused by the amount of fiber present. Now we have completed the fiber length analysis, and next class we will discuss a new topic. Till then, thank you.